In the last video, we stopped right here, tying the idea of the area under the curve to the total distance traveled in a rate time graph. Very important, it's a rate time graph. Now remember, in algebra, you could find the area of the pink stuff right here, which would be a rectangle, but you could not find the area under the exact area under the curve. So in calculus, we are going to find this blue area right here to find the exact distance traveled. Like I said, if you're in a rocket heading out to outer space, you want to make sure that your mathematicians can give you exact numbers, not approximate numbers. You may or may not live, who knows. Okay, so that's what we're aiming for. But first, we have to start out with simpler methods so we understand the more complex methods. Right here, we're going to talk about rectangular approximations. Now, in some textbooks, they're called not left ram or right ram or R ram, L ram. They are called upper and lower sums. Now, L ram is sometimes upper and sometimes lower. R ram is sometimes upper, sometimes lower, and I'll kind of show you what I mean. So, for example, if you have a graph, right, and it's increasing from left to right like this. Let me change that a little bit so it's increasing a little faster. And the LRAM always starts at 0. So right here is going to be the first part of the graph. And then it goes over and then you have your intervals. Let's say these are our intervals. So there's our first rectangle. And then it starts here. There's our second rectangle. Then it hits the graph there. Hits the graph there. That represents the height. Whoops. So right here, there's the height of the next rectangle, and then so forth. So the height of the next rectangle, let's say, is all the way up here. Now, when you're adding the area of these rectangles here, you notice that it is an underestimate. So if the function is increasing, then your LRAM is going to be a lower estimate. So now let's back up a second a little bit and let's look at what if my function is decreasing, meaning it looks something like this, right? And our LRAM, let's say here, 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 and here. So those represent all of our different heights. Oh, maybe too many rectangles in here, huh? Okay, so it goes from here, then here to here. Okay. This can sometimes be tricky to draw. Let me back up a little bit. I drew the last couple of them wrong. Function is decreasing. Your LRAM, if you find the area of all of these, you can see it sticks outside of your curve. Then that would mean that this would be an overestimate or an upper limit. So got to be careful. It's asking for the upper or lower. You got to figure out if it's increasing or decreasing to make that determination. So now let's look at an example of RRAM. We'll only do one here. And we'll do an increasing. Whoops. Again, we want it to increase a little faster. Okay. And then we just set up our intervals. 1, 2, 3, 4, 5, something like that. Now with an RRAM, right, you are going the heights from the right side. So instead of starting at 0, you're starting at 1. And on the LRAM, you notice our last point was right there. It was the next to last point, because right here was the last one, it was the next to last point. But on an RRAM, since it's the right rectangle, the right part of the rectangle is hitting the curve. Ours are going to look something like that. So if it's increasing, the right rectangles are going to be the over estimates, and the left rectangle or the right rectangles for a decreasing are going to be the under estimate because they're going to hit all under the curve. So then you would find the area of each one of these to find the upper limit approximation. And then the MRAM, really, I'm not going to do an example here, but this is basically where instead of the left or the right part of that rectangle hits the function, this is where the middle part hits the function. This is used a lot of times when you want to find the average between the two. And in fact, if you take the LRAM plus the RRAM divided by 2, that would equal the MRAM. So LRAM plus RRAM divided by 2, that's the MRAM. Okay, it's important to remember, like right here, it's always important to remember that these are approximations. It's not exactly the amount of space under the curve. It's an approximation, and obviously the average is going to be the closest approximation than either the LRAM or the RRAM. Okay, so let's look at an example here. We have a particle that starts at x equals 0, moves along the x-axis with a velocity of t squared plus 1 for when time is greater than 0. Where is the particle when time is equal to 5? It doesn't say seconds, but let's say seconds. Now, approximate the area in the curve using 5 rectangles. Right, so that is our interval. That is how many rectangles we're going to put in there on the graph. So first of all, let's sketch this graph. You have your y-axis, which is the velocity. And then you have your x-axis, which is the time. Now, the t squared plus 1 is just like x squared plus 1. So it's going to be up here at 1. And it's going to look like x squared. Something like that. And we're going out to 1, 2, 3, 4, 5 seconds. Or units, it doesn't say specifically. Now, we're going to do LRAM and RRAM. So this is going to be an example of LRAM. Okay, now the first thing I'm going to do, since I know LRAM starts at 0, I'm going to put a point there. Then at 1, then at 2, then at 3, then at 4, and I don't at 5, because I include the first, exclude the last. Okay, so at 1, comes over, 2, comes straight over, 3, comes straight over, 4, comes straight over, and then your last one. That's your 5th rectangle right there. So what we're doing is we're approximating these areas right here. Okay, go ahead and try that on your own. Pause the video, try it on your own, and then come back to see how you did. See how you did. Now here, I like to set these up per rectangle. So a sub 1 is this first rectangle. So these are all the heights. So this is actually the width, sorry. The interval, all of them are 1. Okay, so you would have 0 plus 1, 0 squared plus 1, 1 squared plus 1. Again, I'm using this function right here to determine the heights. Then 2 squared plus 1, 3 squared plus 1, 4 squared plus 1, right? Because these are the heights here. So at t equals 0, 1, 2, 3, and 4. Okay, and then these are the areas, because I multiplied them then by the widths, which are all 1. And we add all of those together, and we get 35 units from the starting position. Now, let's try one for, we did our LRAM, let's do another one for RRAM. So go ahead and set this up just like what we did. We have our graph, and then 1, 2, 3, 4, 5 intervals, and this time go ahead and try RRAM. Pause the video, do this, and then come back. Looking at the right rectangle, so you don't start at 0, you're going to actually start at 1 and end with 5. So 5 is your last height, right? So you know this is, since it's increasing and it's in right, it's going to be an over estimates. This is going to be your upper end, or your upper estimate. So let's go ahead and draw the rest of them in here. Okay. Whoops, not that last one. Sorry. Let's redo that last one. It's from here. Okay. So now when we find those areas, we know it's going to be more than, and remember, we're going to exclude the first, and we're going to include all of these plus that last height right there, and that last height ends up being 26. Sorry, 5 squared plus 1 times 1 gives us 26. So we're going to add all of these together, and then add also 26 to that, and that gives us a total of 60 units from the starting position. So you can see that that is the upper limit. So the actual answer is going to be somewhere between. If you average those, I think you end up getting somewhere around 46 units. So the average is going to be a lot closer than either one of those, as you can see. Okay, let's look at then a word problem here. You're walking along the bank of a tidal river and watching the incoming tide carry a bottle upstream. You record the velocity of the flow every 5 minutes for an hour, with the results shown in the table below about how far upstream does the bottle travel during that hour. We're going to find both the LRAM and the RRAM in this case using 12 subintervals. So all the math is done for us here. We just have to figure out what to do with it. And so if we look at the LRAM, okay. Now remember, LRAM, that includes the first. So in this case, 0, but excludes the last, which in this case is 60 seconds. All right, so when we set these up, you're going to begin at 0. Go ahead and try this on your own. Remember, these right here, if we're looking at the curve, this determines the height of our rectangles. Okay, those are the heights of our rectangles, and these are the widths of our rectangles. Go ahead and pause the video, try this on your own, and come back. This up, you notice that all of these intervals right here are the same. So you can just factor that out, right? So those are all of the widths of the rectangles. And when you add all of these, so for this one, we are going to be adding all of these down to there. That's what I have in there. And when we add all of those and multiply, or so we're not going to multiply yet, but you're going to take 5 times 17.4. Okay, now let's kind of break this down. This is the tricky part. That 5 represents time, and that's in minutes, right? So we're going to look at this because we have to look at units in this one, which makes it kind of tricky. So it's 5 minutes. I'm going to make that as a ratio, 5 to 1, so 5 minutes. Times, this is meters per second, so that's 17.4 meters per second. Okay, you notice when we multiply them, you're going to have something minute meters per second, which doesn't make any sense. All we want is right here is we want to know how far does it travel within that hour. So we have to do something to get rid of both minutes and seconds, and it's an easy fix. So we are erasing time here, which is really cool to think of what you're doing, but you are. You're getting rid of the time in this scenario. So you'd have 60 seconds to 1 minute. That's an equivalent ratio right there. So then when you go through and multiply and simplify, the minutes and seconds will cancel. So you'd have 5 times 17.4, which gives you just, times 60, which gives you 5,220. 5,220. And that is just in meters. So that's how far that bottle traveled given that time. Go ahead and pause the video and try the RRAM on your own and see how you do. We are excluding 0, so we are only putting those and adding those together, which you notice it's going to be just one less since we're not including that one right there. So, and make a long story short, you shouldn't have to do all of this. You should see that and notice that instead of 17.4, it's going to be 16.4. Multiply these all together and you end up getting 4,920 meters. That's it for this